All right, so I think I'm recording. Let's take a look at problem number 26 of our review packet. It's asking us to determine whether this function is even, odd, or neither. I would rewrite it in function notation. And I would evaluate the function at the opposite of x and compare it against this original. So I've got this. If I have a negative base raised to an odd power, it's going to be negative. I can see that this is not equal to the original. So therefore I know it's not even. Had this been equal to the original function, it would have been an even function. We could stop right there. Now let's take the opposite of this, and we get 3x cubed minus 6x. That is equal to the original. So since the opposite of f evaluated at negative x is equal to f of x, we know that it's an odd function. Now, there's some shortcuts that you probably prefer. If you look at the exponents on the variables, if they're all odd, it's going to be an odd function, provided that you have a non-zero constant. I mean that you have a zero constant. That if you're adding or subtracting some non-zero number, it's going to ruin it. It's going to be neither even nor odd. But this guy is an odd function. Let's go on to the next one. So you're probably familiar with what the graph looks like. It looks like a parabola that has been pushed down 3 units. It's been vertically stretched and pushed down 3 units from the origin. Because remember, if we have the graph, we can just look at the graph and look for symmetry. If it's symmetric with respect to the y-axis, it's an even function. If it's symmetric with respect to the origin, it's an odd function. But when they give us an equation, let's evaluate it at the opposite of x, which everywhere we see an x, we replace it with the opposite of x. We simplify that. We have a negative base raised to an even power. It's just going to be a positive. That's equal to the original. So since f evaluated at negative x is equal to f of x, then we know it's an even function. And the exponent is even. And this time, if you add or subtract a value, if you have x squared, say, that's symmetric with respect to the origin, if you subtract, say, 2 units from it, it's just going to push it down 2 units, and it's still going to be symmetric with respect to the origin. So the minus 3 doesn't ruin it like it would have had this been minus 3. It would not have been an odd function. It would have ruined it, and it would have pushed it down, because odd functions definitely have to pass through the origin. Even functions and odd functions have to be symmetric with respect to the origin. If you put your pencil at the origin, rotate the graph 180 degrees, you should still get the same graph. And here, if you look at the right half and the left half with respect to the y-axis, then you'll see that they're mirror images of each other. All right, so what about this one? Well, we see that it's going to be neither because it has both an even exponent and an odd exponent on the variable. But if you're going through the definition, f evaluated at negative x so I can see that this is not equal to the original. So since f evaluated at negative x is not equal to f of x, it's not even. What about the opposite of this? We've got negative x squared minus 2x. Well, the middle terms are equal, but the other terms are not. So since the opposite is not equal to the original, it's not odd. So with this, we say it's neither. So you had an example of each, odd, even, and neither. Hope that helps.